Hello, Flat Earth researchers, debaters and debunkers. A lot of people will spend their entire lives never even beginning to question the official narratives that we hear, and they won't question the so-called scientific consensus that we live on a spherical Earth, assumed to be another planet spinning at about 1,000 miles per hour at the equator, orbiting a massive sun 93 million miles away. Now, the thing is, when you do start to question the official narrative and scientific consensus, you end up getting mixed answers, which are often just compartmentalised scientific explanations, as they say. But when you try to put some of those explanations side by side and compare them, they often contradict each other. And they often contradict the reality that we see, experience, and measure. So one of the fundamental scientific explanations that contradicts other compartmentalized explanations is related to the Coriolis effect, and how we see that apparently happening with Foucault's pendulum, which is a long pendulum suspended from a ceiling, and it is said to be just going back and forth in a straight line. However, to us it appears to do a circle and knock down pins as it completes this circle over the space of 24 hours, because the Earth is said to be rotating underneath this freely suspended object. Now, you could already dispute that by just examining and studying how pendulums actually work in reality, and it's very difficult to get a pendulum to actually go in a straight line back and forth. They do tend to go in circles, and if it's very short, that circle will be very brief, but if the pendulum is very long, then it will take a lot longer to make that circuit. So Foucault could have just made a pendulum that was long enough and heavy enough to do a circle over the course of 24 hours because it's moving so slowly. And of course it is assisted in its swings with magnets just to keep that momentum going. But that was one of the first experiments to really make it appear as if the Earth is spinning beneath freely suspended objects. This is before aircraft came along, really, or even before the jet age for sure. So then let's take that as a given, for example, that the Earth does spin underneath objects that are in the air or freely suspended above the Earth. And we can take that theory and apply it to ballistics. For example, if a sniper has to fire a gun, it is said that that sniper has to compensate for the Earth spinning beneath the bullet that would have been fired in a straight line and will continue to go in a straight line, but will not meet its target if the Earth is spinning beneath it. Now, okay, in theory, that would maybe fit with the Foucault's pendulum, but in practice, in reality, there are no snipers and there are no ballistics experts that ever have to actually compensate for curvature. They just fire directly at their target. Of course, there are various factors involved, but none of those factors are anything to do with the Earth curving or indeed spinning beneath the ballistic missile or the bullet that is traveling in a straight line, and will meet its target if it is aimed at that target. So we have an explanation that fits with that first fundamental one of the Foucault's pendulum, but it doesn't really actually happen in reality. And of course, when we have a helicopter in the air or a hot air balloon or even an aircraft, there is no compensation for any spin or curvature when flying. A helicopter will hover and the Earth will not spin beneath it, and a hot air balloon will get carried along by the winds, not with any relation to whether the Earth is moving underneath it. So for all intents and purposes, everything we do on or above the Earth is done as if the Earth is level and stationary. So when reality demonstrates to us that there is no Coriolis effect present, then we get another compartmentalized explanation that does contradict the original Foucault's pendulum explanation that the Earth spins beneath the pendulum, because then we're told that, oh, the atmosphere is stuck to the globe Earth and spins with it, which is basically to say that it's the same as being stationary, and there is no Coriolis effect all of a sudden. And I've even heard it say that ballistics and aircraft are treated differently, but the fact that an aircraft has its own thrust and can go in any direction it likes means that we can and should be able to go with or against the spin that is assumed to be happening, whether the atmosphere is or isn't stuck to the Earth. But we know that that doesn't happen to the air. As we know with balloons that get carried along with the winds going in all directions, nothing is sticking to the Earth in that respect, and nothing is rotating with an assumed rotating Earth either. The Earth is stationary, and the winds travel across the Earth in all directions, regardless of any assumptions that the Earth is spinning. So all of these explanations start to conflict with each other and with reality. And we know, for example, that aircraft go in a straight line from their departure point to a waypoint or their destination in a straight line. They never ever have to compensate for the Earth spinning beneath them. Pilots treat the Earth as a level stationary plane. It doesn't matter whether you're going with or against the alleged spin, east or west. Flight times are no different in that respect. They may be different because of the winds that you face, tailwinds or headwinds, but at no point or time is a spinning Earth factored into flight plans. And the same goes whether you're traveling in a northerly or southerly direction. You don't aim for a destination that is going to come around to you or go away from you, depending on which direction you're going. You more or less go straight to that destination. So it really doesn't happen for pilots. Now, before we move on, let's just briefly clarify what the Coriolis effect is and how it can be demonstrated. It's often referred to as the Coriolis force, but really that's just a description of what we see happening depending on our point of view. And it's usually demonstrated by having two or more people on a rotating platform, just like a roundabout in a kid's playground. So you'll have two people opposite each other on this rotating platform, but if that platform is stationary, they can easily throw a ball back and forth to each other in a straight line. But once the platform is rotating and one person throws the ball to another opposite them, they will not be able to catch the ball if it's thrown in a straight line, because the person opposite will have rotated past the point that the ball has gone, or the direction that the ball was going. Now, with a little bit of practice, you can end up throwing the ball in a way that it does get caught by the person opposite, but that means not quite throwing it in a straight line, or throwing it in a way that will allow that person to catch it as they come around, rather than missing it because the ball was thrown in a straight line. And the point of view that we have of this scenario will give us these different effects that we see happening. So, for example, if you have a camera looking down at the people on the rotating platform, and the camera is fixed, but the platform is rotating freely beneath it, and one person throws the ball to the other, we'll see the ball travel in a straight line across the screen, but it won't meet the person that is on the opposite side of the rotating platform. And then if we have a camera that is fixed to the platform, looking down again, but it's rotating with the platform, then what we'll see appear to happen is that the ball will appear to curve as it goes through the air. In reality, it's going in a straight line, but because the camera is rotating with the platform, then the ball appears to curve as it goes through the air. Now, if you then take the perspective of one person sitting on the platform and they are ready to receive the ball, we see the same thing happen. The ball is being physically thrown in a straight line, but it appears to curve away from the person who's ready to catch it. So, okay, this is something that can be demonstrated as happening in the real world. We can see the Coriolis effect or the Coriolis force in action. But if we then look at reality and we look at an aircraft going through the sky, either away from us or towards us or anything else like that, do we see that apparent Coriolis force or Coriolis effect? Do we see the object appearing to curve because we are on a rotating surface while that ballistic or the aircraft is going in a straight line? No, we don't see that. We see everything going in a straight line if it is traveling in a straight line. If something is curving, we'll see it curve, not because of any effect that is said to be happening to us on a rotating sphere. So if something's thrown or flown in a straight line, it will appear to fly and be thrown in a straight line to us, no matter where we are looking at it from. So we can see from this demonstration of the Coriolis effect or the Coriolis force that it doesn't fit with what we actually see happening in reality that is supposed to be happening to objects that are freely suspended above an alleged spinning Earth. Now, one thing we see happening in nature that is attributed to the Coriolis effect or the Coriolis force because the Earth is said to be rotating is the direction that winds go either side of the equator. We are told that because the Earth is rotating, winds do not travel in a straight line. They take curved paths. And so a cyclone or a hurricane north of the equator will veer off to the right, whereas those that are south of the equator will veer off to the left. But this isn't necessarily something that can be definitely attributed to the Earth rotating. We can get the same effect if we put an oar or our hand through water, and we'll see vortices occur on either side of the oar going in different directions. The same happens with aircraft wings. You might have seen an aircraft taking off and you'll see vortices on either side, or the top side and the underside of the wing, and they are going in different directions. So really you are talking about something disturbing the air and creating these vortices either side of it. So of course on a level Earth with a local sun, you've got the sun taking its path around the equator, and so the change in temperature is what we know will cause winds to occur, so that as the sun rotates above the Earth around the equator, then that can be attributed to the winds traveling in opposite directions either side of the equator, just as we see the vortices with an oar or the wing of an aircraft. It's the same thing. So this is something that we can demonstrate in reality without having to have the Earth moving or assume that the Earth is moving for that to happen. So I've been thinking about ways that we can test reality and see whether we're on a level Earth or one that's actually rotating. And so I've come up with this flat Earth versus globe Earth physics thought experiment, but also something that we can test in reality. And the question raised here is, which is measurably true according to demonstrable physics? And we have two options. One, we're on a level stationary Earth. That is our default reality. That's how we experience reality. Or number two, we're on a spherical Earth spinning at 1,000 miles per hour, and that is the heliocentric globe model and all those different explanations we've just talked about. Now, some of you may contest number one and say, well, we could be on an Earth that is moving up at a constant speed in order to give us gravity, to give things weight. I'm open to entertaining that idea, got no problem with it, except for the fact that acceleration seems to be the only way that we can recreate the same effects as gravity, as something having weight in any given direction. If something's moving at a constant speed, I don't really see that that would be able to give us weight. So that's my only bone of contention with that theory, I suppose. We can't really go and test it. We can assume it, we can think about it, we can maybe model it if you like, but there's nothing we can really do to prove anything other than what we experience, and that is that we're on a level stationary Earth. So then let's first look at Isaac Newton's first law of motion, which is all about inertia, which basically says that an object at rest stays at rest, just like the coffee cup on the table or the table on the floor. It just stays there. It doesn't do anything. And the second part of that is that an object in motion at a constant speed in a straight line stays in motion with the same speed and in the same direction unless acted upon by an external force. And that is kind of true to an extent. Of course, you can throw your coffee cup and it will go in that direction, or you can fire a bullet or a rocket and it will go in that direction. But of course, it will eventually come back down to Earth because of what we assume to be gravity. So, okay, there is something that makes that not constant. And let's just have a look at those examples of external forces. First of all, we've got friction or resistance, which slows the object. So, of course, if you roll a ball along the floor will eventually stop it from rolling. You've got friction. Or you throw something or drop something through the air, then you've got the resistance of the air itself. Now, when it comes to dropping things, of course, weight is talked about or described mathematically as acceleration. But when we drop something from a high height, it does eventually reach terminal velocity. Now, you could argue that this is because of the air resistance, but it's not something that we can test. So although weight is described as being acceleration, when something is actually falling through the air, it does reach a terminal velocity. So it doesn't accelerate forever. It just carries on at a consistent velocity until it obviously meets the floor. So there's a whole bunch of things to consider there. But then we have this next one. Something pushes the object in a different direction. So that's another example of this external force. So your hands or wind can push something in a different direction than what it was originally going. Okay, that's an external force. And then another example of an external force is an explosive force that accelerates the object in the same or a different direction, like a cannonball, a bullet, a rocket, or a jet engine. And okay, we've got these external forces which we know can change the direction that something was originally going. So let's have a look at when is the first law of motion true. Well, we can say that the results are the same whether we are stationary or moving at a constant linear velocity. So that's important that we differentiate between linear and angular velocity, which we'll have a look at in a minute. So constant linear velocity basically means moving in a straight line with no change in speed and no acceleration or deacceleration. Okay, and yeah, so there's no change in direction either. That's constant linear velocity. So in conclusion there, we cannot feel or measure any difference between standing on a stationary surface or a surface that's moving in a single direction with a constant linear velocity. And for example, we could be jumping up and down on a stationary train, but then that train's moving and we can be jumping up and down on the moving train, and there really is no difference. We jump up in the air, the seats are not going to move away from us when we're on that moving train. So essentially we do indeed move with a train that is going in a straight line at a constant speed. Okay, so then when the first law of motion is false is when an object is moving with a spinning surface or container, and that is angular velocity. So it's ironic, really, that a lot of the time when someone is defending the globe, they will say, oh, well, imagine a train, imagine being on a train. And of course, that's linear velocity. And they'll say that it doesn't matter whether you're moving or stationary, jumping up and down won't make any difference. And they are correct in that respect. But angular velocity is what's supposed to be happening with the spinning globe Earth. So making a comparison with linear velocity is not scientific, really, is it? Because what we should be experiencing is a change in angular velocity when it comes to being on a spherical Earth. All right. So then we could come to this. How can we test whether the Earth is moving or stationary? So I've come up with a method here to compare the results of jumping in 4 different scenarios on a platform with what we experience on the Earth itself. Okay, so here's what we know happens on Earth. Here's the action over here on the left and the result on the right. So if we're jumping up and down on the spot on the Earth, then the result is that we land in the same spot. Okay, so that's the same as being stationary or moving in a constant linear direction. Okay, and then the other action is running and jumping in any direction. So we get up some speed, and then what happens is we land in a different spot in the same direction. So basically our momentum is conserved in that respect. Yeah, you do a running jump and okay, you will travel through the air and land somewhere else, but in the same direction that you were running. Now that external force could be created by a catapult. So we could be catapulted in any direction. And in that case, we would land far away from where we started in the same direction. So again, momentum is conserved. So these are very similar scenarios. It's just with a catapult, we've got that extra force pushing us externally. So from these results, which we can test any time, we can conclude that moving through the air in any direction is equal to the external directional force only. That's just simply what happens in reality, regardless of what you imagine reality to be. That's just the way it is, right? Moving through the air in any direction is equal to the external directional force only. And so let's think about an experiment to test whether Earth is moving or stationary. And let's go with this common argument that you must imagine yourself on a train. So we're talking about linear velocity rather than angular velocity at this conjecture. So we've basically got 4 different things that we could do here to test this. First, we could jump up and down on a stationary platform, see what happens. I think we know that we would just end up being in the same spot. And then number 2, jump up and down on a moving platform that's moving at a linear velocity. So this could be a truck or something that is moving along at a certain speed, and we jump up and down and see what's happening. Is that any different to jumping up and down on a stationary platform? And then the third scenario is to run and jump forwards in the same direction and at the same speed as the moving platform. So you have a platform or a lorry, a truck moving or a train moving in one direction, and if you jump forwards in the same direction at the same speed, what happens? Do you cancel anything out? What happens to you? And then the fourth scenario is to run and jump backwards in the opposite direction and at the same speed as the moving platform. So let's say the platform is moving at 20 miles per hour. You go in the opposite direction at 20 miles per hour as well and see what happens. Now, some of these you might be able to imagine, some might be a little bit counterintuitive, but what we can do is just have a look at some videos to see these different scenarios, especially 3 and 4 here, and let's see what actually happens in those scenarios compared to what we actually have already confirmed and concluded happens in reality, where if we jump up and down on the spot or run and jump in any direction, we either land in the same spot or we land in a different spot in the same direction. Let's compare that reality that we know with these situations here. So in this first scenario, we have someone jumping up and down on a stationary trampoline. So this could be the same as our stationary Earth. And as you would predict, he's just coming down in the same spot because the platform or the Earth or the trampoline is not moving beneath him. In this one, the trampoline is being pulled along at a constant speed by a tractor. And as you can see, the guy is jumping up and down on the trampoline, but he's also traveling along at the same velocity as the tractor. So in this case, there really is no difference to jumping on a stationary trampoline or jumping on a moving Earth. You just go up and down and land in the same spot. And for the third scenario of someone jumping forwards on a moving platform in the same direction and at the same speed as the platform is moving, I couldn't find anyone actually doing a real demonstration, but according to the physics, this is what happens. Basically, you'll end up as a crumpled heap on the floor because you actually push yourself further and faster than you're already traveling. So you won't have a very comfortable landing. So if we just pause here and think about what's happening with the physics compared to the first scenario of being catapulted from a stationary position, it's basically the same. It's just that in this situation, jumping forwards from a moving platform, we don't gain much distance from it because we're not gaining much extra speed. But when we're on a stationary platform and then we are jettisoned forwards, then we'll go a greater distance. But essentially, we are accelerating from our original position and adding speed to it. So if we don't have water to land in to give us a soft landing, then we will hit the ground in a crumpled heap because our momentum has been conserved or perpetuated, and then we continue to travel forwards as we hit the ground. So it will definitely hurt in that respect. And the physics is basically the same, whether we are moving in a particular direction from a stationary position or from a moving platform and we're jumping forwards. And then for the fourth and final scenario, in which we have someone running and jumping in the opposite direction to which the moving platform is traveling and at a speed that's equal to the direction it's traveling. So you're basically cancelling out the speed that it's traveling by moving in the opposite direction at the same speed. We have a scenario that has been tested with real people on a moving platform, and the results are basically at whatever speed you're going. If you match that speed going backwards, in this case they're kind of jettisoning the person from a moving lorry, just like the catapult from a stationary position, but this time they're moving in the opposite direction to the moving platform at an equal speed, and they end up landing just as you would if you were jumping up and down on the spot. So they've cancelled out the speed in one direction by going the same speed in an opposite direction. So in this case, you don't end up in a crumpled heap like you do if you are catapulted from a stationary position, or if you jump off a moving truck in the same direction. So now, with all of these scenarios tested in reality, we no longer have to rely on compartmentalised explanations that contradict each other. We've got results from real-world experiments from which we can draw the conclusion as to whether we are on an Earth that is moving or stationary. So we had these four scenarios to start with, whether we were jumping up and down on a stationary or a moving platform, and then running and jumping forwards or backwards on a moving platform. And so we can then compare those to these scenarios for being on an Earth that is either moving or stationary. So in scenario one, we had jumping up and down on stationary Earth. So that was represented by the guy jumping up and down on a trampoline that wasn't moving. And the results, of course, were that there was no directional momentum. So he didn't get pushed anywhere. Nothing moved beneath his feet. He was just going up and down on the trampoline, landing in the same spot. Okay, and then for scenario 2, jumping up and down on a moving Earth, and that would be with linear velocity or momentum, and that was represented by someone jumping on a trampoline that was being pulled by a truck. So there was linear momentum in that case, and the results there were that linear velocity / momentum is maintained, and it's basically the same as scenario 1, being stationary. Okay, so from these two, you could argue one or the other is happening, but you can't really conclusively prove anything either way, can you? And then in scenario 3, catapulted forwards. And so if that was on the Earth, it would be with spin or with the linear velocity of a moving Earth. And the results there were that actually you would get increased momentum in the same direction, and you would hit the ground hard. You might travel a shorter distance than if catapulted from a stationary platform, though. Okay, so that's being catapulted forwards as if we were going with the alleged spin of the Earth. And then we have scenario 4, catapulted backwards against the spin or linear velocity of a moving Earth. And the results there were that the momentum was cancelled out. You basically safely land directly on the ground as if the Earth was stationary. So in these two scenarios, 3 and 4, we've got a moving Earth or a moving platform, and then we are jumping in one direction or the other to see, and of course the results are different. All right, so in summary, on a moving Earth, we can say that speed and distance traveled through the air when jumping or being catapulted from the ground varies depending on the speed and direction that you're catapulted in. So we would say that accelerating with spin increases your velocity or momentum, and you would have a hard landing. And then if you were accelerating against the spin, that would cancel out the velocity or the momentum that you had, and it would give you a soft landing. Okay, so basically whichever direction you travel would dictate how the landing would be if you're on a moving Earth. All right, and then on a stationary Earth, the speed and the distance traveled through the air when jumping or being catapulted from the ground in any direction is always the same. Okay, so if the platform's not moving or the Earth is not moving, it doesn't matter which direction you jump in or you are thrown or flown in, then it's always the same. You get the same results. So in conclusion, the only conclusion here can be that the Earth is stationary, because in reality, the distance traveled when we jump, shoot, or fly in any direction is always relative to the external force exerted. The momentum / force is always maintained, and we will have a hard landing, yeah, which is very different to what would happen on a moving Earth. All right? There you go. Reality tells us. No scientific explanations required. No models need to be assumed. When you test reality, then it tells you that the Earth is a level, stationary plane. Thank you very much. Click subscribe and the bell icon if you'd like to receive notifications of new videos from Phuket Word.